Hey everyone, and welcome to this explainer on advanced machining. Today we're going to explore the absolutely fascinating non-mechanical processes that engineers use to shape materials when, well, traditional tools just flat out fail. We're talking about the true cutting edge of manufacturing, and yeah, pun absolutely intended there. We're going to leave the saw blades behind and dive into some truly mind-bending technology. Let's get into it. So I want you to imagine a super high-stakes manufacturing scenario. Picture this. You're tasked with carving complex cooling channels into a solid block of heat-treated aerospace alloy. But there's a massive problem. The metal is just so impossibly hard that your drill bits are literally snapping like twigs, and all your usual mechanical cutting methods are entirely useless. So what do? How do you cut a metal that's literally too hard for a blade?
Well, for centuries, machining was entirely mechanical, right? You just used a harder material to chip away at a softer one. But mechanical chip formation becomes completely impossible, or at least highly uneconomical, when your workpiece material is exceptionally hard. Specifically, we're talking over 400 on the Brunel hardness scale. To put that into perspective, that's roughly the hardness of a heavy-duty steel file. Traditional tools also fail miserably when you're working with highly brittle materials, things like glass and ceramics. Or what if the part is so incredibly slender and flexible that the sheer physical grinding force would just warp it or snap it right in half? You can't just power through that.
So how do we solve this? Easy. We bypassed mechanical force entirely. Here's a quick look at our agenda for today. First, we'll look beyond traditional machining. Then we'll carve with chemistry, machine with sparks, cut with lasers, and finally, we'll explore the power of water. Starting off with Section 1, Beyond Traditional Machining. Moving right along to Section 2, Carving with Chemistry. Okay, let's dive into this. Back in the 1950s, the aerospace industry had a realization. They desperately needed material removal efficiency that didn't depend on how hard a metal was. Enter chemical milling. It's exactly what it sounds like. Instead of cutting metal, we use corrosive fluid reagents, think sodium hydroxide for aluminum, to selectively eat away at the material. It's wild. These incredibly intricate, complex shapes are produced entirely through chemical dissolution, without a single physical blade ever touching the metal. In aerospace manufacturing, chemical milling is used to selectively remove shallow layers. We're talking up to 12 millimeters deep, from these huge curved missile and aircraft skin panels. And the best part? It significantly reduces the overall weight of the part and leaves absolutely zero physical burrs on the edges. And it gets better because we can actually combine this chemistry with photography to make incredibly tiny, complex parts. This is a process called photochemical blanking. It's essentially a straightforward four-step process. First, you coat a metal sheet in a photosensitive material. Then you expose your design onto it using ultraviolet light. After that, you wash away the unexposed areas, and finally, you just let your chemical reagent etch away the exposed metal. It's basically exactly like developing a photograph, but instead of a picture, you end up with a flawless, burr-free physical shape. And get this. This works on metal foils as insanely thin as 0.0025 millimeters. So the crucial point is we can manipulate ions to our advantage. And that brings us to electrochemical machining, or ECM for short. Think of it as the exact reverse of electroplating. Basically, an electrolytic fluid, like a highly conductive solution of sodium nitrate, is pumped at massive speeds between your tool and your workpiece. Then we apply an electrical current, and the metal ions are literally washed away from the workpiece before they even have a chance to plate onto the tool. Because it's purely chemical and electrical, there's absolutely zero thermal damage to the part, and no wear and tear on the tool whatsoever. And this brilliantly illustrates why this lack of tool wear is so incredibly important. Just take a look at these cobalt chrome biomedical knee implants. These things require flawlessly polished, highly complex sliding surfaces to guarantee painless joint movement for patients. Nobody wants a rough knee replacement, right? It's notoriously difficult to reach these interior curves with a physical grinder. But with electrochemical machining, a precisely shaped tool gets close, the electrolyte flows, and the high spots are just smoothly dissolved away into a perfect mirror finish in a matter of minutes. ECM is also exactly how we solve massive deep drilling problems. Check out this ridiculous ratio, 300:1. Using a clever variation called shaped tube electrolytic machining, or STEM, engineers use an acid-based electrolyte and a tiny titanium tube to drill cooling holes as small as 0.5 millimeters straight through thick turbine blades. Achieving a depth 300 times the diameter of the hole? Yeah, that would be completely impossible with a standard drill bit. It would just snap. All right, Section 3, Machining with Sparks. Let's shift gears from chemistry to the raw, crackling power of electricity. In electrical discharge machining, or EDM, we are literally eroding metal using rapid, transient spark discharges. And these are flashing at staggering rates, between 200 and 500 kilohertz. We are essentially melting microscopic craters into the material. The only catch is the material has to be electrically conductive. The setup requires submerging both the tool and the workpiece in a dielectric fluid, usually something like mineral oil. Now, this fluid is absolutely critical. It acts as an insulator right up until the electrical potential is high enough to spark. Then it cools the intensely hot area and safely flushes all that vaporized metal debris right out of the gap.
Now, one of the most visually stunning applications of this tech is wire EDM. It basically acts like a glowing electrical bandsaw. Instead of a solid tool, it uses a constantly renewed, highly tensioned brass or tungsten wire. It just slices so smoothly and intricately through solid blocks of metal. We're talking plates as thick as 300 millimeters. And it does it all without ever applying physical force to the metal itself. It's like a hot knife through butter, but with electricity.
So EDM is a total game changer because, again, its efficiency is completely independent of metal hardness. You can cut the hardest stuff out there. However, we have to be real, it does have a distinct drawback. Because the sparks are quite literally melting the metal, it produces a molten and resolidified surface known as a recast layer. This layer tends to be pretty rough, and it lowers the fatigue properties of the metal, which basically means engineers usually have to go back in and follow up with some subsequent finishing cuts.
Moving on to Section 4, Cutting with Lasers.
Now we transition to our third elemental force, light. Laser beam machining focuses high-density optical energy to, well, simply evaporate portions of a workpiece. Now, what's really interesting about this slide is the sheer unbelievable precision we're looking at here. You can see a focused laser beam torch effortlessly slicing intricate floral patterns right out of sheet metal. Because lasers can be focused so tightly, they can pierce holes as unimaginably small as 0.005 millimeters. But hey, don't let that delicacy fool you for a second. These powerful lasers can also reliably slice straight through steel plates up to 32 millimeters thick. It's crazy versatile. And speaking of versatile, lasers are just incredibly flexible tools all around. For one, they don't require any sort of special vacuum environment to work. Plus, they can cut pretty much anything. Metals, plastics, ceramics, composites, you name it. They're often paired up with a stream of inert gas, like nitrogen or argon, which acts to instantly blow away the molten debris right from the cut. They're even integrated directly into mechanical turret punch presses nowadays. That allows a single hybrid machine to punch out simple shapes mechanically and then instantly swap over to the laser to cut out the highly complex curves. Talk about efficiency.
Now, you might be wondering how a laser actually compares to a true particle beam. Well, in Electron Beam Machining, or EBM, we're accelerating electrons to 80% of the speed of light to get extremely precise, narrow cuts, which sounds awesome, right? But EBM has some massive, massive limitations. Namely, it produces hazardous X-rays, so the entire process absolutely must be done inside a restrictive vacuum chamber. Lasers, on the other hand, use photons, so they cut just as cleanly and efficiently right out in the open air of a factory floor.
Of course, when we talk about high-energy thermal cutting, we absolutely cannot ignore plasma arc cutting. By ionizing oxygen gas into a plasma beam, this method generates staggering temperatures. We're talking up to 9,400 degrees Celsius. That is insanely hot. At those kinds of temperatures, you can rapidly slice through solid plates of steel that are 150 millimeters thick, like it's absolutely nothing.
And that brings us to Section 5, the power of water.
Okay, so we've burned it with chemistry, blasted it with sparks, and melted it with lasers. Let's move to our final elemental force. By taking pure water and forcing it at extreme pressures, up to 1,400 megapascals, through a sapphire or diamond nozzle as tiny as 0.05 millimeters, we create a literal, deadly accurate fluid blade. And because there's zero heat generation here, engineers love using robotic water jets to slice flexible materials like vinyl auto dashboards, composites, and even food products. It completely eliminates the risk of warping or burning the material. Let's move to and see how this builds into something truly revolutionary. Enter the laser microjet. This is, without a doubt, the ultimate hybrid tool. It's a totally mind-bending system that uses a microscopic, low-pressure stream of water to perfectly guide a laser beam right into the cut. The water effectively traps the light, acting as a variable-length fiber optic cable. I mean, how cool is that? This setup just separates the labor beautifully. The laser does all the actual heavy lifting, right? It vaporizes the material. Meanwhile, the tiny 25 to 100 micrometer water jet provides absolutely crucial cooling to the heat-affected zone, and it instantly flushes away all the debris and weld splatter. It literally gives us the pinpoint precision of light combined with the cooling safety of water. It's genius. We've really seen how pushing past the physical limits of a metal blade led us to harness chemistry, electricity, light, and water. These advanced non-mechanical processes have completely revolutionized aerospace, medical implants, microelectronics, the whole shebang. But it does leave us with a pretty thrilling question to ponder. If we can sculpt the hardest metals on Earth using just corrosion, sparks, light, and water, what fundamental force of nature will we harness next to build the future? Thanks for joining me on this explainer, everyone, and keep learning.